Problem number 18 is asking us to calculate the volume of a solid that is obtained by rotating a region in the xy plane, which is bounded by the x-axis, the parabola y equals to square root of x minus 1, and the vertical line x equals to 5. This region is being rotated about the x-axis. That gives us a solid pictured on the right hand side of the region, and we need to calculate the volume of the solid. The principle that we will be using to calculate this volume is the one that we've also used in the previous problem, namely that the volume of a solid could be calculated by integrating the area of a cross-section, where you should imagine that the cross-sections are performed perpendicular to a certain axis, and the area of the cross-section varies depending on the location of the cross-section. When the solid is obtained by rotating a region around the x-axis, one possibility is to simply consider the cross-sections of our region by planes perpendicular to the x-axis. A typical cross-section in this case will be a disk of radius that will vary depending on the location. You can see that the cross-sections situated towards the left are going to be small disks, whereas the cross-sections situated towards the right are going to be larger disks. This is our first observation, that the each cross-section all cross-sections are disks of radius. Let's think about the radius. So if I picture the region that, redraw the x-axis to make it a little bit more even. This is the y-axis. Now I'll try to draw the x-axis a bit straighter, like this. Then here's our region. Which is situated between x equals to 1 and x equals to 5. Now, imagine we're taking a cross-section at some point, x between 1 and 5. I'll indicate that by a yellow. Now, what I'm showing here is the cross-section of the region that generates the solid. It's a segment, line segment, vertical line segment that starts at the x-axis and ends on the parabola. Now the equation of the parabola is, remember, y equals to square root of x minus 1. Now the cross-section of the solid by the plane x equals to whatever that value of x is will be a disk, which is obtained by rotating this yellow line segment around the x-axis. And so the radius r of each cross-section will be exactly the length of this cross-section, and since this cross-section goes from y equals to 0, right, this point right here is y equals to 0, goes up to y equals to square root of x minus 1, the length of this cross-section of the region is square root of x minus 1, and then when we rotate that line segment about the x-axis, we get a disk of this radius, square root of x minus 1. Okay, now the area of a disk of radius r, you probably remember this from high school math, and the area equals to pi times r squared. Now r, as we just determined, is square root of x minus 1, and that needs to be squared. And so we get pi times x minus 1. This gives us the area of the cross-section of our solid in by the vertical plane given by the specific value of x. So for instance, if we use x equals to 1, we're going to get, and plug it in here, we're going to get that the area of the cross-section equals 0. That's because at x equals to 1, and that corresponds to the leftmost point of our solid, and there is only one point in that cross-section, so the area is 0. And as we move on to the right, so for example, the rightmost cross-section corresponding to x equals to 5 will be a disk of radius 2, square root of 5 minus 1, and the area of that disk is going to be 4 pi. Somewhere in between 1 and 5 we're going to get an area between 0 and 4 pi. And what our principle says is that if we want to calculate the volume of the solid, we just need to integrate this area of the cross-section with respect to x, because x in this case is the variable that determines the position of the cross-section. And so the volume of our solid will be integral from 1 to 5 pi times x minus 1 dx. Now, of course, I can factor out pi. Pi is a constant. I can pull it outside of the integral, and then it's easy to integrate term by term. But just for the sake of demonstrating the usefulness of making substitutions, I'm actually going to make a substitution here. Not really necessary here, kind of an overkill, but why not, since it's going to kind of simplify things for us. So I'm actually going to make a substitution u equals to x minus 1. If I calculate the differential of u, that would be the differential of x minus 1. Now the derivative of x minus 1 is equal to 1, and so what we will find is that the differential of u is the same as the differential of x. What about limits of integration? When x equals to 1, u will be 1 minus 1, 0. When x equals to 5, u will be 5 minus 1, 4. And so by making this substitution, we get an integral from 0 to 4 pi u du. And now it's quite easy to integrate. Pi is a constant, pull it out, integrate u with respect to u, you're going to get u squared over 2. And then we just plug in our limits of integration, 0 and 4. This gives us, when I plug in 0 for u, the result is 0. So we get, our final result will be pi times 4 squared divided by 2, 8 pi. Now, here be careful, the problem is asking of what you need to enter. The problem says the volume is an integer multiple of pi, in other words, pi times an integer. And the question is, what is that integer? And we see that that integer is 8. So the number that you have to enter for this problem is 8.